Hope the screen is visible now.
Yes, sir.
Thank you. Yes. So probably we are at the penultimate section of compilers, which talks about machine independent compiler features. In the previous class, we talked about machine dependent compiler features, which were mainly focusing on how effectively we can utilize the various contents that processor deals with. So where we looked at the intermediate form of the program that can be used to reduce maybe any redundancy in the structure, maybe in terms of generating blocks or removing or rearranging the various quadruples such that the effective utilization of the memory that is a part of a registers of a processor can be explored. So that is mainly on the content of the compiler, which is depending on the architecture perspective, because anything that we talk about registers processor, obviously it is under the control of a processor or architecture. Thereby that part was discussed as mission dependent compiler features. One, having a blocks, dividing the given program into various blocks, and we know each block is an independent structure, independent execution, no loops are involved. And second, rearranging the quadruples such that the transfer of data between memory and processor is reduced to the extent possible. We have taken an example of our variance calculation in the previous class, and you would have appreciated or observed how the interchanging or rearranging of the quadruples will enhance the efficiency of the code. So that's what precisely under the mission dependent compiler features. Now let us get into the mission independent compiler features. There are plenty of features available under this, but we'll be looking at a couple of features which are more visible from our day-to-day programming perspective. So before we go to the mission independent compiler features of code optimization, there is a concept called as a structured variables. The structured variables, I will give it as an assignment, probably later date, because assignment in compilers is yet to be given. Probably I will give a separate assignment maybe by end of this week, where structured variables, you can take it as an assignment. So what do you mean by structured variables here? So compiler will be having lot of data structures involved in the programming, and compiler need to manage all those, which you already seen in the data structures. You use lot of data structures like arrays, linked list, trees, and stuff like that. So here we take an array as a structured variable, as a data structure. How the compiler is going to generate the intermediate code or the subsequent code for the given program. So that is the idea here. Precisely here things are, if you take an array, array can be either row oriented array, a column oriented array, which you might have seen in data structures of array while discussed maybe in second semester, row major address or column major idea and stuff like that. So that is what precisely structured variable involved. And also when we know the array base address, how to calculate the addresses of subsequent elements depending upon the data type. So that is also part of your discussion there, where a higher address minus lower address plus one and stuff like that. So all those things are there, which are going to be part of the structured variables, which are already seen as part of your data structures. So I will not be discussing that at this juncture. I will give it as an assignment. So where time permits, go through that. So before maybe by end of this week, I will be providing that as an assignment. So structured variables is all about how compiler is going to deal various data types or data structures such as arrays, linked lists, and trees. But here we take arrays as an example, which is simple and which is familiar to you, where how arrays are declared, what is a row major order or a column major order, and how to calculate the given array of integers, how to calculate the address of subsequent values, and once the base address is given. So that's what precisely is structured variables. So you can take it as assignment. So next part is mission independent code optimization. In the exam, you will get a question either for a mission dependent code optimization or mission independent code optimization. 8 to 10 marks, you will definitely have a question on this. So it is very important. First, not to have a confusion. So mission dependent means, just now we have discussed that it deals more or less or mainly with the processor of the system or the architecture with which we are working. So thereby we have a blocks dividing the given program into various blocks. That was one concept. Second was rearranging the quadruples. Both deal with the processor or the registers of the processor, more specific. Thereby those two are concepts of a mission dependent compiler features. Now coming to the mission independent, as we know, notice there might be more than 5 to 6 methods, but we'll be concentrating only 2 methods out of this. Let us see what are those concepts that come under the mission independent code optimization. So mission independent code optimization has 5 to 6 varieties, in which the first two are very important. That is elimination of common sub-expression. We are discussing this as a mission independent code. That means not depending much on the architecture here. So thereby these things come under mission independent code optimization. First one, elimination of common sub-expressions. Is it possible to eliminate some common expressions or loop variants? For example, you might have taken a for loop for I is equal to 0, I is less than or equal to 10, I plus plus. At the same time, you write for j is equal to 1 something. So let us say in ADA also we might be using extensively these 2 to 3 levels of for loops. So when you are in the very inner level, let us say when you are j, and any time unless I value is changed further, that means when you go to next iteration of I remains constant. So if you are calculating say 2 into I, 3 into I, 5 into I, or I plus plus, I remains constant throughout the inner loop of j until I gets further incremented. For example, I is having variation of 1 to 10, j is also having variation of 1 to 10. So when I is equal to 1, for all values of j is equal to 1 to 10, I remains constant. So if at all is there any expression or a statement involving a sub-expression of a I, which you are used at multiple places within j, you need not calculate that more than once, right? Because I value remains constant throughout the j loop, because I is a outer loop for the j. If that is the case, unless there is a completion of one iteration of all the values of j, you will not be incrementing value of I. So during that particular time, any expression involving y which is repeated more than once in the j loop need not be computed more than once. So that is the concept of a elimination of common sub expression. So that expression can be calculated only once. That is an idea. We'll go in deep to understand what it is. So that is the first one, elimination of common sub expressions if at all they are existing. Second, removal of loop variants. Again, this is similar to the elimination here, but more so with the loops. In loops also, again, we might be having the similar structures. That means these variables might not be what you call required more than once. Maybe the duplications probably similar to that. So removal of loop variant is also very important. We'll also see that in detail. Next, we have a rewriting the source program. So normally you might have heard teachers telling you can write an efficient code by in one single shot by using shorthand notations and stuff like that. So rewriting the source program precisely talks about, can I reduce the length of the program from 10 instructions to 8 instructions by using all possible techniques that are available in the given architecture or given programming language. So rewriting precisely is more so restructuring the entire program so that the duplication of calculation can be reduced. This is one method, rewriting the source program. 99% you will be writing a efficient code. If at all, if it is possible, probably we can reduce redundancy and remove redundancy if possible, and make sure that in one single sentence or one single statement we can achieve multiple values. So this is nothing but which will get over a period of time as and when the program is getting executed on trial and error method. So rewriting the source program is also one of the technique for the optimization of the code. And fourth one, substitution of more efficient operation for lesser efficient one. So we keep hearing that this could have been the better choice in the place of this. For example, when you talk about sorting, There are so many sorting, and we know which is the best sort. All will do the same result. All will give the same result, starting from your bubble sort till your quick sort and radix sort and heap sort. But each one have their own plus or minus. So if somebody asks you which is the best sorting algorithm you can choose, probably you can say I may go for a quick sort. But other sorts are also equally good when it comes to their own territory. So depending upon the various constraints what we have, so is it possible to replace the given particular code with a better code? So that probably again as a programmer we need to look at the concept. That's why it is coming under the mission independent. So mission has nothing to do with this much, but we need to make sure that efficient operation can be used in the place of a lesser efficient one. So we can help the compiler to have a better efficiency through this. So one is rewriting the program, other one is replacing the less efficient instruction or a construct by more efficient construct or the operation. Next two things are very generic in nature. Folding, that is, can we have performing of all this data at compile time itself? That is, normally we postpone to runtime because data is given during runtime, and examples of will reveal that this data will be executed based on the instructions what you have. So is it possible to make sure that most of the computations can be done at compile time? So we will not have much burden at the runtime, or any errors can be easily, because we know that the semantics part of your compilation is very critical. Many times you feel program is very good, everything is fine, but result is not correct. That you might have experienced in ADA, because teacher would have told there is a array boundary problem, that's why you are not getting result. It is taking some junk values, you're getting minus values, it is going beyond the limit, all those things. But if you look at the program looks very, very simple, and program looks very, very right, but the result is not correct. People say that there is a logical error in this, or a semantic error, or a runtime error. So why we are calling them? Because those things are not identified at the compile time. So if possible, try to figure out those things and make sure that they can be identified, because what is happening at runtime cannot be easily identified by us. So we need to trace the program properly by giving various inputs and keep on tracking what is happening at each stage. Then only we can figure out any runtime errors or the logical errors. So better not to go to that level and avoid those instructions or those computations. Instead of postponing to the runtime level, better to do in a compilation. If it is possible, we can go for that. That is a concept of a folding. Another possibility is loops. So there are a lot of code is around the loops in any programming language. Loops are having their own plus and minus. So if read baby, we can combine more than one loop. I mean, suppose if a program is having two or three different loops are branching, is it possible to combine? That is called as a loop jamming. So loop jamming is nothing but merging of various loops into one. Whereas a loop unrolling is what? We have a normal code, convert that into loop if it is required. So like we have to do normally, a program is converted, divided into multiple functions. Teacher would have said that, okay, write a function in the place of a normal code. So converting into a loop is nothing but a unrolling of a loop, a converting or merging more than one loop into one single platform is called as a jamming of loops. These are various methods. You need not be worried too much here, but just understand that for mission independent code optimization, we exist so many. Why? Because these are all in the hands of the programmer to majorly. So wherever possible, try to help the compiler to make sure that the code is optimized. But we'll be concentrating on the first two, that is elimination of common sub-expressions and removal of the loop variants, as two important concepts under the mission independent code optimization. So from exam perspective, you have two under the mission dependent code optimization of a compiler. On the other hand, we have two more in the mission independent code optimization. So there is a sufficient room for confusion here. So you should avoid the confusion, because the first part is dependency, which is more revolving around the whatever the processor registers we have. On the other hand, mission independent, there is no much interference of the processor here. It is in generic in nature. Is it possible to reduce the duplications from the loops and other stuff point of view and increase the efficiency. Let us see each of these two one by one. So first one is elimination of common sub expression. So this is what I was highlighting earlier. Elimination of common sub. These sub expressions need not be in the loop. They can be anywhere in the program. But all the value is remaining constant and it is not changing. For example, you declared constant int a is equal to 10 or constant int pi is equal to 3.14. And every time you will be writing, say, 2 pi r, 2 pi r, 2 pi r. So many calculations you are doing. So 2 into pi is a constant there. 2 is a constant, pi is a constant, only r is changing. If that is the case, why unnecessarily every time I need to compute 2 into pi into r, 2 into pi into r? So what system will do now? System will compute 2 into pi, keep it as a intermediate value, then only multiply that value with this, then probably the result is given. So that is an example of a elimination of common sub expression. You cannot eliminate as a program. Please remember that. So program is there, that is perimeter is equal to 2 pi r, whatever it is, but that you are going to give it to the system compiler. So during the computation stage, during the compilation stage, during the execution stage, it is not going to execute every time 2 into pi into r, since 2 and pi are constant throughout the program or maybe throughout the loop where we are using, then only r value will be changed. So probably internally 2 into pi is calculated and kept as a common expression, only r will be multiplied later. But as a program is concerned, yes, that need to be there because that's what we are going to execute or compute. But internally, system will be identifying, as far as the code optimization is concerned, can I remove or can I eliminate multiple executions of a given expression which is commonly used on second case, which is not changing otherwise. Then better to have a expression separately, and because once computed I can reuse the data. So that is an example of a elimination of common sub expressions. So this is one such example. If you look at this, we have taken 2 into j, a of 2 into j, again it is coming in b of 2 into j also. In both the cases 2 into j is a constant. So what is the point here calculating 2 into j twice? Need not be, because j value is a constant, because loop is only from I is equal to 1 to 10. J value remains constant. So better to have a j value common here, because 2 into j is like a 2 into pi for us. So this value remains same, and once you compute that, I can reuse every time. I need not compute that. That is a concept of a elimination of common sub expressions. So probably you can look at this example. This is just from understanding point of view. Don't worry. From exam point of view, if you write example of this category, that is more than enough. To understand, let us see. Let us take array which is 2-dimensional here, x to y, 1 to 1, 1 to 10, 1 to 10, and expression is like this. Same expression we have taken here also. So 2 into j is common here. So when you take that, for this entire loop, let us say if you write the quadruples, you will get so many quadruples, because same expression has to be continued for I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, and stuff like that. If you observe here, probably through your eyes, you can make sure that there are certain instructions, there are certain quadruples which are same, ditto, no change at all. They're same. For example, if you take 5, star is operation, 2 is operand, j is another operand, I3 is what? It is the intermediate, just a name, no change, no problem. Just check, is there any other instruction, other quadruple which matches exactly? So if you come to line number 12, you see the same functionality. Multiplication, number 2, j. But only difference is, instead of I3, we have I8. So I3 and I8 are only intermediate names. They are not going to be very crucial. But what is crucial here is multiplication operation, operands involved. They remain same here at line number 5 and 12 for the given array of this category. So what is the use? There is no point in repeating 2 quadruples for the same functionality. What could have been done here? Replace line number 12, rather remove that, but have the values of I3 and I10 same. So whenever you calculate I3, you can also reuse that I3 at line number 12 without computing again and again. Similarly, we can see some computation of this category here, maybe at line number 6 and line number maybe 13, you can see here. So subtraction operation, maybe even 6 and 7 is also almost same. So subtraction operation, I3, I4, number 1. So wherever there is a constant values which are not changing throughout the program, probably they are the best fit to be eliminated as a expression or a sub expression. So thereby this 20 line program what we have can be reduced subsequently maybe to 15 or 16 depending upon removing how many we are going to remove here. So this program now, if you carefully observe, you can remove some 3 to 4 sentences, and if you look at the next diagram, the 20 becomes 16 here. So 4 statements we have reduced. So that is what the concept of a elimination of sub expressions. So when you eliminate the sub expressions which are duplicate in nature, which need not be, see, if you look at here, the 2 into j is computed only once instead of computed twice in the previous diagram or previous concept. It is computed only once, thereby the same value can be reused again and again and again. So that is the concept of a reusability here, where we are going to remove the sub expressions which are redundant in nature. So removal of the sub expressions which are going to be redundant in nature. That is an idea behind this. Again, we can see very clearly that 20 has become 16 only. Okay, where we are reducing 4. So when you reduce the 4 instructions, obviously your program is saved by 20%. So saving a program length by 20% is not a small amount. It is going to impact on the efficiency of the program from time perspective as well as from the memory perspective. So this is the idea behind the how we are going to eliminate the sub expressions which are common in nature or which are redundant or duplicate in nature. Next, so this is what just put in a small form. So entire program what we have here we could not take, so I just represented from exam point of view. We can write like this. Okay, so where one common expression is enough for us to compute. Okay. Next, so that's what the 2 into j in our example is a constant that need not be computed multiple times, and this is just explanation for the concept so that you can easily understand. So thereby we are going to eliminate all those sub expressions which are common in nature, and hence the code can be optimized. So which is an example of a code optimization through mission independent form, because we are not talking any registers here, we're not talking any processor here, we are just removing multiple calculations of the same data. So we are the execution level only we are going to reduce them. So it will never go to compiler at this point of time. So thereby it is beyond the architecture control, and hence we say it is a mission independent concept of a code optimization. So second one probably will also be in similar lines, but we will be more worried about the how to control the loops. If any similar to what same concept or same example we can look at here as well. In loops also, if there is a possibility of having a variant or a variable which is executed more than once, in such cases probably we can do. Same example holds good here as well. And the previous one need not be as part of loops, but this is more so with the loops to make you comfortable. The same example has been taken. So when we need to calculate the data only once inside the loop or even outside as well, then probably we can compute. That's what we have seen in the first case. Second case is more specific. How there might be chances that a loop might have some constant value like this 2 into j, which need not be computed every time because it is getting reused in other form as well. So in such cases, again, you compute it only once, you can reuse it in the other places. Thereby we say, is it possible to remove any variations or any variables that are part of the loop? That's what we did precisely here. So removal of loop variance is also an important concept where we can reduce the what you call calculation of duplicate variables or duplicate instructions. Thereby we can reduce the dependency on them and increase the efficiency of the compiler. So that is another way, that is removal of the loop variance. It is also very easy concept where wherever possible examples of this category are there, then probably we can remove them and calculate only once. Thereby we can extend the what you call the availability of registers for other activities, and enhancing the efficiency of the code is going to be feasible in these cases. So these are the two concepts which come under the mission independent code optimization. Okay. So this is the process. This is just explanation as we discussed now. The 2 into j, which is again a common here, can be calculated only once. Thereby, it need not be repeated or repeated calculations of the same value variable or 2 into j construct can be avoided. Thereby, optimization of the code is increased. So these are the various methods, various ways with which we can look at code optimization. So any doubts at this point of time, probably can let me know, because these two are very important concepts as far as the compiler is concerned. Thereby, any doubts here should not be there with you. Maybe confusion with respect to code optimization, or having any what you call concepts clarity missing here, probably can let me know. Take attendance meanwhile. Asta,
Yes, sir.
Abhinav, Aishwarya,
Present, sir.
Amrish,
Yes, sir.
Anu,
Present, sir.
Arjun.
Present, sir.
ಏನ್ ಅರ್ಜುನ್ ಸರಿಯಾಗಿ ಬರ್ತಾ ಇಲ್ಲ?
Sir, like my grandma, no, she is not feeling well, sir.
Okay, okay. Arbaz, Ashok, Benita, Bhargavi,
Present, sir.
Bhavisha,
Present, sir.
Chaitra,
Present, sir.
Chatterjee,
Present, sir.
Diksha,
Present, sir.
Deepika LG,
Present, sir.
Deepika MB,
Present, sir.
Murli Krishna, Gangubai,
Present, sir.
Guriya Kumari,
Present, sir.
Harshit,
Present, sir.
Junjar Singh,
Present, sir.
Kavya,
Present, sir.
Kishore,
Present, sir.
Lata, Manisha,
Present, sir.
Manjunath,
Yes, sir.
Nayana, Nilanjan, Nishant,
Present, sir.
Pavitra,
Present, sir.
Maithili,
Present, sir.
Priyanka,
Present, sir.
Pavan, Akash,
Present, sir.
Rajeshwari,
Present, sir.
Rakesh, Ramya,
Present, sir.
Rashmi,
Present, sir.
Ravishankar,
Yes, sir.
Rizwan,
Present, sir.
Vishal,
Present, sir.
Savita,
Yes, sir.
Ji,
Present, sir.
Sneha,
Yes, sir.
Spurti,
Present, sir.
Srinidhi,
Present, sir.
Srinivas,
Present, sir.
Sunil,
Present, sir.
Vaishnavi,
Present, sir.
Vinny,
Present, sir.
Sir, Abhinav present, sir.
who is that?
Abhinav.
Benita, sir.
Abhinav, yes, yes. Vinita, done.
Okay, sir.
Yeah. Fine. So next concept is compiler design options. This I will postpone to next class. So before that, let us look at some of the programs. We started somewhere with the Lex and Act, how compilation is done. Since we know fairly about how the processing of compilation works, let me take some examples of our Lex and Act, and will let us observe how these Lex and Act tools are going to help us. So let me check once. So now I will present my PM player. Let me know if it is visible to you. Hope it is visible.
Yes, sir.
Yes. So I've just created some programs here, and these programs are mainly for understanding Lex and Act. So let me repeat the Lex program that we had earlier. So this is the, okay, one second. So the Lex program, what we had last time is vowel. So this is the program we had. And we know that AE, IOU was vowel. And what is not AE, IOU? Hope it is, screen is visible to you?
Yes, sir. Yes, sir.
Yes, yes. Because
Sir.
it's are very small here. Okay. Let me see if it can increase. Click. So this is a program. So if you look at, this contains 3 sections. This is the section of a definition where it is similar to the C program. Then we have a last section which is user subroutine section, which is also similar to C programming. In between we have a rule section which talks about regular expressions, how my rule should be looking at. So our requirement was AE, IOU, AE, IOU. So let me execute this. So to execute, Lex is the command, name of the program. And once execute, when there is no error, it will create another file called as a lex.yy.c. And since it is a C program, I will be executing it as a C program, that is GCC. And I need to club the C program with the Lex library. So I will add one more option called as a -ll compared to the normal C program execution, because our requirement is not C alone, it is also a Lex library. So because Lexer is what is going to be used. Now let us execute. When I execute, the program is executed and no errors here now. Compilation is done. So now we'll execute the program. So a.out. So we know when I give a.out, the program gets executed. If you remember, we have written enter the text. So I will write now, hi, where are you today? So I have given this now. So can you tell me what is the output now? How many vowels and how many consonants? What is the result we can get here? How many vowels? How many consonants?
Ten vowels.
10 vowels. How many consonants?
Nine, sir.
Okay, fine. Don't worry. Keep that number with you. Now let me execute. So since it is a standard input, I need to press Control D. Let me press Control D. So we are getting 10 vowels and 15 consonants. So Spurti, can you say why 15 consonants? So your count is not matching here. Any reason why?
So I think space included.
Yes. So what is the rule now? We have given the rule that what is other than AEIOU is going to be consonant. So what is other than AEIOU here? Space is there, question mark is there, enter is there. So they all get participated in the consonants. Now remember the text what I have given. I will alter the program. Let me see how best we can do that. If it is going to make some sense to us. Let me see if it is going to make any sense. Hopefully it should not be error. That means what I was trying to say is it is possible to close our grammar properly so that you will not end up in having such type of issues. Okay. Okay, rule cannot be matched. Fine. Fine, but that is possible. Maybe some syntax error here. So probably what I am trying to say here is that even though dot, space, question mark, enter are not consonants, in our current program it is being shown, but it is possible to control that and make sure that only actual consonants are part of it. So for that we have a small code there. Maybe we need to recover that, but otherwise it is possible. So what you have to keep in mind is that you specify the grammar to that specification. It is possible to provide the rules that we have to keep in mind. So this is what we have seen from a Lex point of view, which is a scanner, which is a tokenizer, which provides lot of tokens being generated, and it is the first stage what you have seen. Now let us get into next concept called as a ACK, that is YACC. So YACC is a expansion for yet another compiler. This is one of the compiler design. The next topic what we will be seeing is one like this, YACC, yet another compiler. That is the name we have. So this is acronym for that particular concept, which is ACK, YACC. So I've written some program already. Let me see what is that. Maybe string, not EXPR. So I will open that program where I have used that EXPR, which you have been using for a long time, calculation of how expression should look like. So this is a Lex program. So Lex is a analyzer for tokens, whereas ACK is a parser. So when I am going for one stage to another stage, so Lex is the first stage, so it doesn't require any other input. Whatever input we provide, it makes into tokens and says whether those tokens are right or not. But when I go to the next stage, that is a parsing stage or syntax analysis stage, whatever that I have generated from Lexer is going to act as an input to the parser or the syntax analysis stage. Thereby, when I talk about ACK, that is YACC, I require the support of a Lexer. So that is the reason why whenever you develop a program for a ACK, we need two programs. One is the Lexer program, other one is a ACK program. Simply because syntax analysis also requires the output of a previous stage, that is the lexical analysis. So this is the lexical program or Lex program rather. If you see here, it is not having all the three sections. It has only first one, that is a rule section. It has only, first one is definition section, second one rule section, the other one, the third one, user subroutine section is not there because it is not a Lexer alone. This is just a communication between a Lexer and ACK. Lexical analysis is combined with the syntax analysis. Probably when you write a ACK program, there we'll see the user subroutine function. But here we are only informing the system that, look, I have identified this as the tokens, and these are the tokens which you can use in the syntax analysis. For that communication purpose, we need to create. So what you have to see here is Lex is a lexical analysis tool, ACK is a parsing or a syntax analysis tool. For a syntax analysis, we also require the initial stage or first stage information. That means for any ACK program, we require a Lex program also. So this part is clear for us. We are including tab.h because y.tab.h is a ACK program. This is not your typical hash include type of characters where we have stdio.h, but it is a y.tab. Y.tab means every Lexer, if you remember, when a Lexer creates, it creates a table. What is the table? The table contains two columns. First column is what is the token? Second column is what is the number? For example, printf 25, if 46, left parenthesis 29. For every string that we have identified as a token, there will be a corresponding number which call it as a tab or tabulated value. That value will be stored here. So these are the values that are part of this, and this we are including for the purpose of a ACK program. So that is idea behind. So y.tab.h, what does it contain? It contains all the tokens which are there as part of the Lexer and their corresponding values, and those values are submitted as input to the ACK. Now, and we are telling that what is the token? How do I identify a token? So whenever I see 0 to 9, since it is an expression, my program is my expression program. I have identified anything between 0 to 9 and plus. Plus means one character or more than one character. So if that is the case, I can write 00, 056, so repeat these numbers more than once. If that is the case, I say 0-9 plus. Then whenever I say this is going to be identified as a num. So num is a token here. Similarly, when I see other than these numbers, I am going to return 0, meaning that I don't want to take anything other than num. So if that is the case, I want to ignore that. Similarly, dot here, which we tried earlier. So return text dot yy text dot yy text is one of the keyword here. Don't worry too much at this point of time. Assume that whatever we want here is only token here. Anything other than this is going to be ignored. If that is the case, we are going to write this. That's what we are trying to tell from a lecture point of view, where we can write very specific grammar here. So lecture has been written now, but that is not sufficient because we need to combine this with a ACT program. So now let me open the ACT program. So what we are doing in the lecture now, we are just identifying which are the tokens. What is the token here? Num is a token which is having the value 0 to 9 or groups of or sequence of numbers like 0 to 9, right? Let me look at the ACT program now. So gedit expr.y, because since it is ACT program, extension is y. Since it was a lex program, extension was L. So now this is ACT program. ACT program is also pretty same as the lex. It contains 3 sections: definition section, rule section, user subroutine section. Since we need to combine lexer and ACT for a given program, this combination is what is going to identify the communication between lexer and ACT. So we are telling, if you just remember, just now we have created a num as a token. But how do ACT will come to know there is a num which is a token? So we need to inform that this is a communication now. Percentage token is a keyword, which is a keyword we have used now. Num is a keyword that we have used. And we are going, since it is expression, expression will contain plus, minus, multiplication and division as operators. And we have to tell them what is the associativity. So percentage left or percentage right, we can write. So when you see them, the associativity is from left to right. That's the concept what we're talking here. So if you want, you can remove this, but since we want a very clear expression without any ambiguity, we can keep on adding all those. Now this is actual grammar. What is this grammar now? I'm talking about expression. This you can relate with your Pascal language, what you have taken. If you remember, assignment statement is ID is equal to EXPR. EXPR can be term, factor, multiplication, division. If you remember that, we have written expression in similar lines. So expression can be expression plus expression, or expression minus expression, expression multiplication expression, or expression division expression, or it can also contain the parenthesis, and finally it can be num. So what we observed here earlier is whatever you see on the left hand side is a non-terminal symbol. Hope you remember that. So EXPR is a non-terminal symbol. So here we are not keeping in angle brackets because it is a program. This program does not support angle brackets. We have kept in while discussing because that for you to make sure that which is a token, which is a non-token. That was only a convention for understanding. Since it is a program, whatever you see to the left hand side of a colon, you can see a colon here. Whatever you see left hand side of a colon is a non-terminal symbol. Whatever is there on the right hand side of a colon can be a non-terminal symbol or it can be a terminal symbol. If you look at num, num is a token. Token is nothing but a terminal symbol. So this is same rules what you have studied, we have used in the ACT also. If you have any doubts, please let me know or I will continue further. So assuming you don't have any doubts, so next we will go to the next section, which is a subroutine section. If you remember here, in the lex we have used yy lex. Now we are using yy parse. So if yy parse gives 0, that means my expression is a valid expression, else I will be printing invalid expression. So what is our interest here is how an expression can be identified. An expression can be a number alone. You can see or operator here. It can be a number, or it can be within parenthesis, or it can be with plus, minus, multiplication, division. So this is what the concept of expression we have identified. Now let us see whether our inputs, whatever we give, is going to give us a valid expressions or not. If this is done, we'll compile in the same form. Let us go to the stage. Now lex has to become compiled in the same form. Lex expr.l. Next, ACK is the command for that, and we need to write expr.y. Since ACK need to take those tab.h, if you remember, we need to give this D. So D is an option which will club this lex and ACK from the that y.tab.h perspective. So we are going to do that. So this is also done, no errors. Since it is a C program, what I get at the end of the day, lex.yy.c for a lexer. Then we'll have one more C program for a ACK. So y.tab.c. Since there are two programs, one is for lex, one is for ACK, then we combine them with the lex library as usual. If successful completion, no errors, then /a.out. So this is the program. Okay. If I press hi, how are you? What will happen? What could be the result when I press hi, how are you here? Is it valid or invalid? If I give hi, how are you? Will it be valid or not? Because my lex program is expr, my ACK program is expr. It's valid or not? Okay. It's invalid simply because my expr contains num. Num is nothing but 0 to 9. So unless I give 0 to 9, anything other than that is a invalid expression. So this is actually part of our syntax analysis. This is what you see. Whatever you write printf, it should be like printf only. If any character, if you replace, on the other hand, it will say it is a invalid, some error will come. So that is actually the outcome of a syntax analysis. Now let us see. Let us give 2. Is it 2 valid or not?
Yes, sir. Valid, sir.
Valid. So we are getting a valid expression. So 2 plus 3, valid or not? It's valid or not? It's valid, right? Next, A plus B, valid or not?
Invalid, sir.
Invalid because it is only 0 to 9. So A plus B looks like 2 plus 3. It looks like expression, but we have defined it as a numbers, not as a characters. Probably if you modify that, we can have it. But right now, it is not valid. So it is a invalid expression. So let me take this. It's valid or not?
Valid, sir.
Valid. So it is a valid expression. Valid or not? Because every operator should have something on either side. Expression plus expression, expression minus expression, expression multiplication expression, expression division expression. So on either side of the operator, we need to have something. Since I am not having any value, this is a invalid. So like that, you define a grammar, you define the rule, and your input will be mapped like this. So this is the idea with which your syntax analysis works. And for every instruction or construct of a programming language, we need to develop a grammar of this category. So this is the idea behind how we can look at the syntax analysis. Okay, let us take one more example. Hope this is clear to you how lexer and ACK communication is going to provide us the seamless compilation stages. Okay, let me take one more. probably I have str. Yes, I have another program by name str, gedit str.l. This is what we have taken a power n, b power n, where n is greater than or equal to 0. So this is a different program where for me, I want to write, we have written so much of automation theory. Now we are representing in a ACK form, syntax analysis, if it is valid or not. So a power n, b power n, where n is greater than or equal to 0. So a, small a means I'm considering this as a token. This A, capital B are tokens. If you want, you can write anything. Small a and b are my input. If you want to say small a is donkey, small b is horse, you can write. You have liberty. I'm just writing a for a, b for b for our understanding. But you can write anything you want. A, b is immaterial. But what is important here is the small a and small b. So we have represented a and b as my actual input. So this is a Lex program. Now similar to that, we have a ACK program which combines. If you remember, we have defined two tokens. So token A, token B. In the previous program, there was only one token, token num. So now the rule is very simple. If you look at here, we have written such a big program, written such a big automata diagram, but look at this now. Very simple instruction, simple line. S is a non-terminal, left hand side is defined as what? A, again S, B. It is a recursive definition. Or since n is greater than or equal to 0, since I need to write, nothing is also a valid expression. So what is the meaning of this now? I can have any number of A's followed by any number of B's. And if I have 10 A's, I should have 10 B's. If I have 20 A's, I should have 20 B's, because n is greater than or equal to 0 and a power n, b power. If n is 2, it should be a, b, b. N is 3, a, b, b, b. If that is the case, this particular single sentence is going to match all those. Very simple to write, but it has a lot of input internally which deals with the recursive or maybe a recursive grammar what we have for the symbol S non-terminal. So A followed by B. Within that we have S. S can be AB, 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 AB like that. So let us see how it is going to be. Other parts are remaining same. So our interest is how input is going to be. So now let us execute same process. Lex str.l, next ACK -d str.y. So we have got C program, GCC lex.yy.c. We have another program y.tab.c, and we need to link with the library. So if everything is fine, then probably ./a.out. So we can execute now. Let me give 2 + 3. So 2 + 3 is not a valid here because we need A's and B's. It gives invalid expression. So now I have A. Is it valid or not? A power n, b power n, n is greater than or equal to 0. When I have written A, there should be corresponding B. Alone A, alone B are invalid. So it is invalid. If I write B, invalid. If I write AB, it is valid. If I write AA, BB, valid. So for every A, there should be corresponding B after A's. So like this. If I write say A, only 2 B's. This is not going to be valid because n is 3 and somewhere n is 2. So it is going to be invalid. So like this, we can develop our grammars in a simple sentences, but they have a lot of value internally. But whatever the possible inputs you mean to have as a confirmation or matching, you need to think and write the grammar. So grammar may look very simple, but they give a lot of inputs. So you can see that all what we wanted are getting executed. Now I will not give anything. I'll just say Control D. It is going to be valid because n is greater than or equal to 0. So every time when you add any impurity or any change in the data, your diagram is going to be bigger. We have already seen in the automation. Now here also your grammar is also be more complicated. So this is how the actually the Lexer and ACK or Lex and ACK are going to be used as a tools. So hope you could understand what actually the Lex and ACK will be doing from the compilation stage perspective, and this is how it is going to be. So if you have any doubts, please let me know. Otherwise, in the next class,